Welcome to the fifth video in the Let's Calc series. Today we're going to be focusing on going through questions from the fifth problem set, at least that's the plan. The fifth problem set focused on the intermediate value theorem and manufacturing continuity. In this video, I've got a series of questions that I think are representative of a little bit of everything. We'll look at one of the first couple questions, which asks you to straight up apply the intermediate value theorem, and use that information to determine some information about a function. We'll talk about the ones where you're asked to explain whether or not you can apply the intermediate value theorem. We'll talk about it. We'll give you an example of the manufacturing of continuity and giving you a tricky one, and we'll even use Desmos to kind of help illustrate it. Then we'll look at a free response style question that's really meaty and packed with really good stuff, but also some really challenging pieces that bring together all the stuff from today's lecture, as well as both topics. So without further ado, let's jump into the first question. And no surprise, the first question that we're going to be addressing is question number 1, which, while the first question typically tends to be a pretty straightforward and doable question, this is packed with a lot of good stuff. So what we're asked to do here is, or what the question says, it says let h of t equal that rational expression. It says to apply the intermediate value theorem to prove that h of c equals 0 for some x value c in the interval from 0 to 5. Then find the value of c for 0 to 5 that satisfies the intermediate value theorem. So, before we jump in, it's worth taking a moment just to kind of talk about the things that you need to do, as well as what the intermediate value theorem says. So, just as kind of a reminder, the intermediate value theorem says the following, and I'm going to move this up over here. What the heck? Let's see if I can write it all in. So, intermediate value says if f of x is continuous, for x values between x equals a and x is equal to b, and f of a is less than or equal to let's say k is less than or equal to f of b. In other words, we're saying that there's some function value k that's between the two endpoints. And for this case, this would be a place where I might say, without loss of generality, we could also say f of b is less than or equal to k less than or equal to f of a. It doesn't matter which order they fall in. So if f is continuous for those x values, and f of a, or k is between f of a and f of b, then f of x, or let's say f of c, equals k for some c in a to b. So basically what this is doing is it's guaranteeing us that there is an x value that has a particular y value. And it does so by asking for two things: continuity on the interval that we're interested in, and boundedness of those endpoints. Whatever y value we want to prove is there must be bounded by the left and right endpoints. It could be the right and left endpoints as well, it doesn't really matter. So in other words, if we want to use the IVT, so to use the intermediate value theorem, we need to do two things. First, we need to verify. I'm going to say prove, but we need to, in fact, I'm going to change it to verify. What the heck, I'm sitting here. Why not? It's my summer, I do what I want. We need to verify continuity. And this first example, it's going to be a little bit of a challenge because verifying continuity is sometimes challenging. And second, we needed to demonstrate, I'm going to use the fancy words, I like these words. We need to demonstrate boundedness. So we need to show that the y value we're interested in is actually between the two endpoints. And bounded just means between. So we need to show it's in between the two endpoints. So that's what we need to do. And then finally, this is kind of a hidden last step. I'm using dashes to write this in here. The third thing that we want to do is then formally state. We need to actually do everything correctly here. We need to say it in the correct way. We need to invoke it properly. There's lots of good words to describe what we need to do, but we need to actually say everything in the correct way and communicate our understanding of how the intermediate value theorem and these properties guarantee us what we're looking for. So as I said, this first question is meaty and packed with a ton of information. So jumping in isn't going to be easy. We're going to try to accomplish all these different things. So when we start things off, I want to focus first on continuity. I want to make sure that this isn't a trick question and we're actually allowed to apply the intermediate value theorem to this function on this interval. So to start with, we're interested in h's continuity. And in particular, we're interested in h of x being, or h of t being continuous on the interval from 0 to 5.
So to start that, we focus on issues that might prevent continuity. So looking at our rational expression, I see a polynomial over another polynomial. The only way a rational expression can be discontinuous is if the denominator is equal to 0. Even if there's a whole, the denominator's the denominator's 0 going to 0 still causes the problem. So what I notice is that based on what I see in this function, there is a vertical asymptote for h of x, or h of t, at t equals -6. So, gasp! It's not going to work. We can't use the intermediate value theorem because there's a vertical asymptote. Not so fast, my friends. Because that vertical asymptote is at -6. And suspense ellipses here for a second. That's not in the interval that we're interested in. So in a sense, there's a problem, but it's someone else's problem. It's just not an issue here. So for us, what that means is since that vertical asymptote, the only discontinuity issue for this function h of t is not in our interval, we can therefore state that h is continuous for 0 to 5. So that's a good first step. What we've just done is we've just verified that this function is continuous on the interval we're interested in. That is the first step. We can't apply the intermediate value theorem without continuity. Otherwise, we won't be able to, quote-unquote, connect the dots. We won't be able to go from here to here and guarantee everything in between. So very important first step. That was us verifying continuity. And in fact, let's see if this will let me do this. I'm going to actually change the colors here so you can see where those pieces came from. So let's make this a nice robust red. Okay, so there was our first move. We've shown that the function is continuous. Our next move is going to be to demonstrate boundedness. And once again, I'm going to take advantage of color and help you see what it is we're doing here. And hope you realize that I'm going through this in much more depth just because sometimes these kind of proving things and communicating things can be really difficult to catch in the flow of a lecture during class. So hopefully that's okay. You don't have a choice because I'm going to do it anyway. I already did it. So from here, the next move is to demonstrate boundedness. We want to show betweenness. So in order to do that, we need to calculate out what the y values are at each endpoint. So first I'm going to calculate h of 0. Looking up at our function, that's going to be when we plug in 0, so 0 squared minus 10 times 0 plus 21 divided by 0 plus 6. That's going to be 21 over 6, also known as 7 over 2. So, great. Thanks for playing. We found h of 0, but h of 0 in isolation does nothing. We need to also compare it to h of 5. So if we plug in 5 up there, we get 5 squared minus 10 times 5 plus 21 all over 5 plus 6. That's going to be 25 minus 50, which is negative 25. Here, I'll keep track of it over here. Negative 25 plus 21 over 11, which is going to amount to negative 4 over 11. Again, but now that we have both endpoints, we have some good information in here. So again, I'm just going to put a little conjunction in there just to illustrate that there are two things. So we've calculated h of 0, we've calculated negative 4 over 11. And our question asked us to prove that h of c equals 0 for some x value in that interval. So at this point, we're ready to finally invoke it. Because what we just showed, and again, I'm going to write this once and then erase it, or go do it again, but bear with me. What we've just shown is that h of 5 is less than 0, which is the h value or y value that we're looking for, is less than h of 0. So that means that we've just shown boundedness. So not only do we have continuity, we also have boundedness. So that means the second step is required. So we've done everything, we've shown everything we needed to, everything is good to go. The only thing that remains for us to do and accomplish is to actually say it all in the correct way. It's like someone's given you the best notes in history for a speech. Everything is there, all the ingredients. No, better yet, let's go to a kitchen analogy because I'm starving. Everything in your kitchen, you have the finest ingredients in the world. Might as well be from the Master Chef kitchen. But you don't have a gourmet dish unless you put the ingredients together in the correct order. That's what we need right here. So let's do it. So in stating our thing, in a sense, this is almost a statement of the proof, or whatever, however you want to think about it. So I'm going to start by declaring what we know. Since h of t is continuous, and I can't just say h of t is continuous because it's not continuous everywhere. H of t is continuous on the interval from 0 to 5. So in a sense, we proved that right here.
Hi there. And since h of t is continuous on 0 to 5, and h of 5 is less than 0 is less than h of 0, by the intermediate value theorem, and I'm going to abbreviate IVT here. I'd love if you wrote out the words, but bear with me for the moment. So, and again, look at how we just did this. We had two properties, continuity and boundedness. We said since h is continuous and bounded, basically, by the intermediate value theorem, h of c equals 0 for some c in 0 to 5. So that right there, this is the proof that we needed. Like, that's the statement that I'm looking for. That is that formal statement step. But keep in mind, you couldn't just get the points for making that formal statement. You also need to verify continuity and demonstrate boundedness. So all the work up here is the work that I'm going to be searching for in your work, or looking to have narrated. So in a sense, we've just answered the first part of the question, and yes, it was a challenge to get there. Like, it was not easy to get there, but we have it. That leaves us one last piece. It says then to find the value of c that satisfies the intermediate value theorem. And I'm not going to ask you to do this every single time, but for here it feels appropriate. So in looking at the pieces that we have here, we want to figure out where h of t is equal to 0, which means we want to figure out where t squared minus 10t plus 21 over t plus 6 is equal to 0. So factoring some pieces here, that numerator looks to me like it factors to t minus 3, t minus 7. And the denominator is, of course, t plus 6, so nothing does whole away, so that's fine. And if that's true, that means that we have two values that make h of t equal 0. We have t equals 3 and t equals 7. So I know you're tempted to start writing things out there, but no, don't do that. We can't say that both those values are guaranteed by the intermediate value theorem. Both 3 and 7 do not satisfy the intermediate value theorem. Why? We were interested in the interval from 0 to 5. Everything in this problem was about guaranteeing there's a value of x between 0 and 5. So 7 is not between 0 and 5. And what that means is bye-bye 7. So the only value guaranteed is t equals 3. So with that in mind, we have now used the intermediate value theorem to prove that there's such a 0, and we found the only 0 guaranteed by the the intermediate value theorem. So there's a big one. Everything's set though. Hopefully that's clarified and showed you all the expectations here. Yes, this is a lot, but no, I'm not going to ask you to do this more than once on a test. So just keep that in mind. Hopefully it's been helpful. Okay, that brings us to question number 4. We're going to look at the two questions, the two parts of question number 4. Question number 4 states, for each function f of x below, explain why the intermediate value theorem cannot be used to show that f of x has a 0 on the indicated intervals. So before we jump in, I also have to explain our reasoning. Before we jump in, let me just remind you that the intermediate value theorem does a lot more than guarantee zeros. It guarantees any y value between those two endpoints, assuming we have a continuous function. So while we're focusing our attention on zeros in both question number 1 and question number 4, hopefully you recognize in the assignment that questions 2 and 3 do not focus on zeros, and you can jump through that proof just as well as anything else. I don't think it's particularly difficult once you've mastered something like number 1, which is a little tougher. So for this one, we're looking to apply the intermediate value theorem. Remember, the IVT applies. Oops, I'm using brown. I'd rather use purple. Sorry, Adrian, my student from the class of 2016, 15, who loved the color brown. So in here, we want to talk about the intermediate value theorem. There's two things the intermediate value theorem requires: continuity on the interval of interest, and also boundedness. We need both of those two things here. And in this case, we're not looking for a formal proof of any kind. We're just looking to explain whether or not it works. So to jump in here, we're on the interval from -5 to 0. That's probably going to play a role. Before I do too much heavy lifting, though, let me just factor it all out, just in case that's going to help me. I get that f of x is 3 quantity x minus 4 over x plus 3. What I notice is that since x plus 3 is in the denominator, there is a vertical asymptote on f of x at x equals -3. So now that might not be a problem if -3 is not in our interval. But unfortunately, our interval is from -5 to 0, which means that our vertical asymptote is in the middle. So in truth, it doesn't matter if we actually have a 0 in this interval. We don't in this case, but there's a chance that we might. What this tells us is since there's a vertical asymptote, so as there's a, here, I'll write this properly. I'll be as proper as possible. As f of x has a vertical asymptote, I don't know how to say asymptote, I don't know, has a vertical asymptote, at x equals 3, excuse me, x equals negative 3, f is not continuous on the interval we were asked about from -5 to 0. So for that, cannot use IVT. So there is our thinking. We can't apply the intermediate value theorem because we just showed that f is not continuous on that interval. So straightforward, pretty simple to go through, but it really did pay off to be able to analyze that function a little bit and look at its discontinuities. Okay, next that brings us to 4b. 4b looks, this looks like an easy problem. F of x is a quartic polynomial. Polynomials are continuous everywhere. So in a sense, right before we even start here, f is continuous. Not just on -1 to 3, but everywhere. Polynomials are everywhere continuous functions. So it's like, this can't be bad. Maybe it's a trick question. But there are two properties. That second property is boundedness. So we need to check and verify that f of -1 and f of 3 bound 0, since we want to guarantee that f of x equals 0. So let's try it. If we plug in -1, we get -1 to the 4th minus the -1 plus 2. That's going to be 1 plus 1 plus 2 is 4. Look at calculus. 1 plus 1 plus 2. So great. On the other hand, let's try f of 3. So we get 3 to the 4th minus 3 plus 2 is 81 minus 3 plus 2, which is 80. So continuous, we got two y values. This is all great. But here's the problem. Those two guys, 0 is not between them. So in other words, the two endpoints don't bound this function. And again, don't worry if there is a 0 or not. That's not the question we were asked. We were asked whether or not the intermediate value theorem would guarantee us a 0 on this interval. And since 0 isn't between those two endpoints, we haven't chosen an eligible interval. So in this case, we want to say these things. Since f of -1 and f of 3 do not bound 0, so there's no sign change. Some people like to say it that way too. That's fine too. Since f of -1 and f of 3 do not bound 0, we cannot use, therefore can't apply the IVT. So basically it just means the intermediate value theorem is not a tool that we're eligible to use in this case. It's just not helpful. It just is. So there we go. There's 4b. Okay, that next brings us to question number 6. Question number 6 is a pivot. We're no longer talking about the intermediate value theorem, although don't forget about it. It will come back again. In question number 6, we're asking you to manufacture continuity. And what we mean by that, of course, is we want you to find particular variable values that will allow a function to be continuous. So now in the assignment, I believe on question number, let's see what are the questions here. On question number 5, I was a little lackadaisical with the way I did this. I'm going to show this as carefully as possible. Now this is more work than I actually expect you to show when you're doing this problem, but I'd rather be thorough than anything else. So if you'll recall before we start, in order for a function f, or in this case we'll say g, is continuous, or in order for a function g to be continuous at an x value at x equals 2, there are 3 properties that we would need. First, we need to show that g of 2 is defined. I guess we need to say this. Second, we need to show that the limit as x approaches 2 of g of x exists. By the way, this is something you should know. And third, we need to show that g of 2 equals the limit as x approaches 2 of g of x. At that point, we could say that therefore g of x is continuous at 2. So in order to do this, if I'm going to be as careful as possible, I should probably go through all these different steps. Now you'll notice that there's a particular step in here that's going to be the crux of this problem, but for the moment, let's do every single step and see what we need. Maybe we can even talk about which steps are most important. So step 1, we first want to show that g of 2 is defined. So in our case, g of 2 is going to be what we get when we plug in 2 to the function. Now in here, x is less than or equal to 2 means we use the cubic portion of this function, which means g of 2 is 2 cubed plus 2b times 2, which is 8 plus 4b. Did that help us at all? Sorry. But hey, we got it. That's nice to know. And a plus 4b is defined, assuming b has a finite value, that is defined, so it's good enough. Our second step, we're curious about the limit as x approaches 2 of g of x. Now for this case, we have a piecewise function whose boundary is at x equals 2. So we're curious about whether or not those two pieces are coming together. So in here, that means what we need to check is we need to make sure that the left-hand limit is equal to the right-hand limit at, of course, the boundary, x equals 2. So given that, we need to check the two one-sided limits. So we'll first evaluate the limit as x approaches 2 from the left side of g of x. The limit as x approaches 2 from the left side of g of x is going to be familiar. It's going to be what we get when we plug it into the first portion. And I probably shouldn't even bother writing this because we already did. But we're going to get 8 plus 4b. Again, not very helpful yet, but patience. Next, we're going to evaluate the limit as x approaches 2 from the right side of g of x. So that's going to use the linear portion, which is going to be 10 times 2 minus b squared, which is 20 minus b squared. Now at this point, we finally reached a place where we have some essential information. If we want the limit to exist, a limit as x approaches c of f of x exists if and only if the limit as x approaches c from the right side is equal to the limit as x approaches c. Oops. Trying to rush through it, sorry. X approaches c from the left side. So we need the two limits to be equal to each other. So in other words, if limit as x approaches 2 of g of x exists, those two things must be equal to one another, which means 8 plus 4b has to equal 20 minus b squared. Now that first step up there, this guy, might not have been helpful. This is huge. We have a single equation with a single variable b. That's a huge thing for us. So what does that mean that we get to do? It means that we get to actually solve this equation and we can finish the problem. We don't even have to finish that final step, although it will of course be true. So in looking down at our little equation here, this isn't a trivial one. I'm going to have to do a little bit of heavy lifting. So I'm going to do a couple different things. I'm going to add b squared to both sides. I'm also going to subtract 20. Now that might feel like a weird choice of moves, but watch what happens. On the left side, we now have b squared plus 4b, and then plus 8 minus 20, which is minus 12. On the right side, we cleared it all. We have 0. That means this is the equation that tells us whether or not b, or how to, this is the equation that contains all the information about what we need of b in order for g to be continuous. So if this thing factors, which it does, because I carefully designed it so that it would, you're welcome, we get b plus 6 times b minus 2 is equal to 0, and it appears we get two values, b equals negative 6, or b equals 2. Now that might feel a little weird for you for the second. It might just seem like that's impossible. How is it possible that we could get two values where this piecewise function becomes continuous? But I'm prepared for you to ask that question and have that curiosity. Here is our piecewise function put in with a random value of b plugged in. At first you might say, hey, but that looks really continuous. Does it now? Does it? You sure? You sure? Sure it's continuous? It don't look so continuous anymore. So in this case, what we saw though is that there were supposedly two different values where this thing became continuous. So let's take a look. Oop, crossed a little bit there. Right there. Oh, look at that. B equals 2. It looks like those pieces came together. There it is. Nicely continuous. It works out really nice. Looks like it might even be continuous at 2,16. So there's one such value. And again, bigger numbers don't work. They start to diverge from one another and go away. Smaller numbers don't seem to work either for the moment, and you're like, oh, this isn't going to work, but look. Suddenly, it starts to slow down, and am I low enough? No, I'm going to make it off. There we go. right there. B equals -6. They kiss together and end up okay. Not okay, and then they diverge once again. So it does look, in fact, like there are actually two values of b that make this particular function continuous, which is pretty darn impressive to me if you ask. And you can't because I'm talking to a digital camera. But there is question number 6 in its full glory. Okay, finally, that brings us to question number 8. Question number 8 was a new creation for this assignment. I think it's an amazing question, honestly. I think it does a great job of evoking the sort of feel that you get when you're doing some free response questions in the actual AP exam. And it's hard in Unit 1 out of like 6 or 7 to be able to really get that feeling. But question number 8 does it. So let's see here. First, in question number 8, it says, consider the continuous function j of t. Values of j of t at various values 1 to 8, so in other words, t is between 1 and 8, values of j of t are given in the table shown above. Well, on my picture, it's below. Sue me, on your paper, it should be above. Use the table to answer the questions below. Cool. So, question A. Like, the table itself looks nicely simple. Other than that, let's jump in. So, question 8A says, what is the minimum number of t values for t between 0 and 8 for which j of t equals 0? So, a couple things here. We're on an assignment focused on manufacturing and the intermediate value theorem. My thought is, right now, I want to use the intermediate value theorem, because we're talking about y values, and we want to look for some sort of thing that will between this. I'm not going to be as formal as I was earlier, because this is asking us slightly different questions. It's not asking us to prove or verify anything, it's just asking us what is the smallest number of t values where j of t is 0. So in here, a couple things. First, j is continuous. And again, since I'm thinking intermediate value theorem, I think it's important to do. How do I know j is continuous? It was given to us. They told me it was continuous right here. Consider the continuous function j of t. That's awfully generous of them, because otherwise it's just a bunch of random points. So good stuff. So we know continuity. What we'd be looking for is we'd want to show j of a is less than 0 is less than j of b. We want to show that there's boundedness. And since 0 is in between, we're looking for something to go from negative to positive. So in other words, in our table, what we want to see is we want to see sign change between x values. So in looking at the table, let's see if we can find some. I found 1. So one interval from 2 to 3, there's a sign change. So since 0 is between 9 and -1, by the intermediate value theorem, since j is continuous, there must be a value where j of t equals 0 on that interval. Likewise, from 4 to 5, we go from -3 to 5. So 4 to 5, we could do the exact same sort of proof and explanation. From 5 to 6, we go from +5 to -2. There's a sign change once again. So there must be a 0 for j of t on there. And then last but not least, from 6 to 7, we go from -2 to 4. So once again, there has to be a sign change. So given that, we need 1 0. J of t is guaranteed to have at least 1 0 on each of those intervals, which means that there must be at least 4 such t values. Actually, I'll just say at least 4 such t. That just seems like a pretty fun phrase to say. Actually, I'll write it this way. So there should be at least 4t. And again, in your explanation, you could talk about the intermediate value theorem guaranteeing continuity. For the moment, I just wanted to talk conceptually. If you're interested in how to state it a little more formally or how I might have stated it more formally, you can look at the written solutions. But there's 8a. Okay, 8b. 8b is the classic IVT question. Is there a value between c between 7 and 8 for which j of c equals 10? Explain your reasoning. So in looking here, let's reason it out first, and let's try to cut out some of that extra work at the beginning. So here is j of t on the interval from 7 to 8. So j of 7 is 4, j of 8 is 13. Now in my mind, I'm going 4, 13. Does 10 fit in the middle? Of course it does, at least assuming we're still able to count. So 10 fits in the middle, and we have a continuous function j of t, which tells me that the IVT will give us the answer yes. So now as far as our statement, we're trying to minimize things here. Let's say it correctly. So since j of t is continuous, and again, not just on an interval, on every interval, so j of t is continuous, and let's see here, j of 7 was the smaller one, so and j of 7 is less than 0, less than 10. See, I almost fell into that trap of saying 0 automatically. is less than j of 8. So we've guaranteed continuity and boundedness. It's a good two things. By the intermediate value theorem, there is a C in 7 to 8 such that j of C equals 10. Done. So that is using the intermediate value theorem and making the statement formally. Notice we didn't have to do much more than think about where 10 falls in relation to 4 and 13, and then state those two properties that we needed: continuity, boundedness. Voila. Okay, that brings us to question 8c, another new question that I'm pretty proud of asking, even though it's very simple to do. The question for 8c says, evaluate the limit as x approaches 4 of j of t. Explain your reasoning. I should probably say provide a reason for your answer, but whatever. Okay, so in here, the limit as x approaches 4 of j of t. So there's 4 in our table. You're probably thinking, oh no, it's a trick. He's going to trick me. We're not supposed to know anything about that specific point, or that specific point doesn't tell us anything about the general behavior. While I agree, and that is absolutely true, we have one new thing that's here. We have a continuous function j of t. So because j is continuous, that means, by definition, that j of 4 has to equal the limit as x approaches 4 of j of t. That's literally the third step of the definition of continuity. So with that in mind, we can state, since j of t is continuous, and again, it's continuous everywhere, so it's therefore continuous at x equals 4. Since j of t is continuous, the limit as t approaches 4, I put an x there, I gotta fix that, I'll fix that later. Limit as t approaches 4 of j of t equals j of 4. Again, only true because j is continuous, and j of 4 is -3. And our explanation is literally those words, j of t is continuous. So voila, pretty straightforward. Okay, so that brings us to 8d. We're looking at 8d here, trying to figure out what's going on. 8d starts with let p of x equal the piecewise function with x squared plus 5 for x less than or equal to 3 and j of x for x greater than 3. Find all values of x for which p is discontinuous, then classify each discontinuity. So as we look at this, there's an important consideration. So first of all, we can state before anything else, both x squared plus 5 and j of x are continuous. So the first one is a polynomial, the second one is defined as a continuous function for us in the problem. So basically that means the only boundary could interfere. So the only discontinuity possible here is at the boundary. So what we need to consider is what's going on as x approaches 3. So we're going to check for continuity at the boundary. So p continuous at x equals 3? Let's try that. At x equals 3. Let's find out. So the first step for continuity is we need to have p of 3 defined. So p of 3 is equal to 3 squared plus 5. Again, I'm looking at the piecewise function, seeing what's in there. We get 14. That's perfectly well defined. I'm happy with that. The second step, though, we need to use the left and right hand limits because we're trying to make sure that these two things match up. So doing this a little bit faster than normal, the limit as x approaches 3 from the left of p of x is going to be equal to 3 squared plus 5, which is 14. The limit as x approaches 3 from the right side of p of x is going to equal not p of 3. It's going to equal j of 3, which is equal to, up here, -1. So what we just showed is that those two limits do not equal each other. So the limit as x approaches 3 from the left side of p of x does not equal the limit as x approaches 3 from the right side of p of x. And yet otherwise these functions are nice and continuous everywhere. What that tells us is that we have a jump at x equals 3. Which means, of course, that this function is discontinuous at x equals 3. Voila. And I can't show you this on Desmos, by the way, because we don't know anything about j except for these random function values. So that's all you get. That brings us to our final question, 8e. Not 80, that'd be a lot of questions. 8e. So in this case, you're once again provided a piecewise function. We've got, it looks like, a polynomial portion, a linear portion with a missing slope and y-intercept, and a rational portion, which could be interesting. And our task is to find m and b such that u of x is a continuous function. So in here, a couple pieces to look at. First, for continuity, like you'll notice that I often do this, and I should do this every single time. If we want to make this a continuous function, we need to make sure it's continuous everywhere, that there are no issues in any of these pieces. So of course, as I look, x cubed plus 2x and mx x plus b are continuous automatically. I just realized that this is a broken question because it's not even connected to the actual problem. That's frustrating. Oh well, let's do it anyway. So both those things are connected and continuous. And then the other one, 10 minus 8 over x, has a VA at x equals 0, but not for x greater than or equal to 4. So basically, once again, we are perfectly fine continuity-wise. All that we need to do is actually guarantee that this is, continuity-wise as far as the three branches go. We need to guarantee continuity, though, at the intermediate spots. So let's do it. Why not, huh? Let's do it. So in digging in here, a couple things to look at. You've done this before, but we'll stick with it nonetheless. We need to make sure that each boundary works and that each step of the continuity is true. What I'm going to do, though, is I'm going to remember back what we just did on that earlier problem. I think it was right, where was it? It was here in question number 6. When we focused on number 6, we realized that even though it's important to know that we are defined at each of those points, what really matters are the left-hand and right-hand limits being equal to one another, so that way we can guarantee the limit exists. In truth, the limit is the difficult portion of this problem. So for this case, I'm not going to do the first step. I'm just going to focus on the limit existing at both x equals 1, the first boundary, and x equals 4, the second boundary. So bear with me as I jump in. So as I do this, we're going to do the limit as x approaches 1 from the left side of u of x. When we do, we're going to get 1 cubed plus 2 times 1, which is 1 plus 2, which equals 3. Yay, calculus. Second, we're going to get the limit as x approaches 1 from the right side of u of x. When we do, we're going to get m times 1 plus b, which is going to be m plus b. Now, in order for these two, for the limit to exist here, so basically I'll say this once, if the limit as x approaches 1 of u of x exists, then the left-hand and right-hand limits must be equal, which means m plus b has to equal 3. So that's going to be an essential piece of information for us. That was our first piece. Let's do it for the second boundary. So at x equals 4, what do we have? We're going to have the limit as x approaches 4 from the left side of u of x. As we approach 4 from the left side, that's going to be using these smaller values, which are going to be from the line. So this will m times 4 plus b, which is going to be 4m plus b. And similarly, the limit as x approaches 4 from the right side of u of x is going to use the bigger values. That's clearly right here. That was the part that was supposed to be a function of j, but we're already here. So this is going to be 10 minus 8 over 4, which is equal to 10 minus 2, which is 8. So in other words, this piece then tells us if the limit as x approaches 4 of u of x exists, that means that 4m plus b has to equal 8. So there's our second piece. Now at this point, we've done all the calculus we need to do, so we can step away and focus on solving this system. We have two linear equations with two distinct variables. We can solve this using one of our linear system techniques. So specifically, if m plus b equals 3 and 4m plus b equals 8, I can multiply this first equation by -1. That'll leave me -m minus b equals -3, and 4m plus b equals 8 because we didn't touch that one. When we add these two equations together, we'll get 3m. No b's left over. It's kind of sadly like the world right now. B's are disappearing. And then finally, we'll divide by 3, which means that m is going to be equal to 5/3. So cool. Works out really nicely. but that does mean that we've only found m. We need one more value. If m is 5/3, then we can pick out either of these equations. Doesn't matter which one, so I'm going to choose the second one, because I think in the written solutions I chose the first one. So 4 times m, oops, I wrote 5. That's how errors happen. 4 times m plus b is equal to 8. That's going to be 20 over 3 plus b equals 8, which is 24 over 3, which means b is going to be 4/3. So supposedly, if we have m equal 5/3 and b equal 4/3, we should have a nice continuous function. I did not put this in Desmos, but again, it's my time, so we can do what we want. So I'm putting this in. We have u of x is equal to, let's do this all correctly. So looking at our pieces here, we've got x less than or equal to 1, x cubed plus 2x. We've got for 1 less than x less than 4. We have mx plus b. And again, we have a b value up there, so we'll be playing with this in a second. Move that down in a second. We can get rid of the first one. No, let's keep it. So that brings us there. And then finally, we have one more piece. For x greater than or equal to 4, we have 10 minus 8 over x. So again, we wouldn't have been able to do this at all if not for the presence of, if we'd used j of x like I was supposed to. But remember, so there's where we start. We're looking at our function here. We were told that the values we wanted was m was 5/3. So let's put that in there, 5/3. Doesn't do anything just yet. But then b equals 4/3. Oh, look at that. It's not the smoothest guy here, but you know, there's some iffy things happening right there and there. But any other value, anything else moves this thing along and kills our continuity. Whereas right now it appears we have in fact manufactured a continuous function, which is exactly what we wanted. And with that, that ends our work for today. Hopefully this has been helpful. I apologize that the floating head in the corner is a little bit iffier in the background because I filmed the video a little bit later, so the green screen's not working. But in any event, hopefully this clarified some very important mathematical concepts. And as always, thanks for watching.